Alright folks, here's section 7.2, the mean and standard deviation of the sample mean. So, we use distributions to make inferences about the population mean based on the sample mean. Now, what we've learned, or what we will learn, is that we can use a normal distribution to make an approximation of the sampling mean. So, remember what a normal distribution is. It has a general shape of a normal curve, and it's determined by the mean and standard deviation. Now, a lot of times, we will say that we will label the population or the mean period with a mut, and we will label standard deviation like this. Now, if we're talking about regular mean and standard deviation, that's how we're going to write it. But if we're talking about the sample mean and the sample standard deviation, you need to write that sub x bar down here. We call it a sub x bar. So it's got a subscripted x bar. So keep that in mind. So if you see me write that, this is talking about the mean and standard deviation of the sample. This is talking about the mean and standard deviation of the population. Okay, so keep that in mind. All right. What is the relationship between the mean of the variable and the mean of the variable under consideration? What is the relationship between the mean of the variable and the mean of the variable under consideration? Well, they're actually equal. Okay, so when you're studying population and population mean, the sample mean should equal the population mean. The sample mean should equal the population mean. In other words, for any particular sample size, the mean of all possible samples, the mean of all possible sample means equals the population mean. So, mean of sample means equals the population mean. Equals the population mean. So, let's look at an example. So here we have our same problem with the starting 5 basketball players. Determine the population mean. Now we did this back in the last section, and we found out that mu is 80. The population mean is 80. Add all of these up and divide by 5, and that's going to give me 80. Okay. Now, obtain the mean of the sample means for the sizes, for samples of size 2. And what we want to do is we want to verify that, what we want to do in letter B is we want to verify that this is true. We want to verify that this is true. So, how to go about doing that? Well, this is where you need to pull out the table from our last section, and this is the table I'm talking about. It's got sample, it's got heights, and it's got your sample mean. And I gave you this is of size 2, okay, of size 2, and I gave you all of these 77.5, 78.5. We found all of these in the last section on the video. It's the table I told you to write down because we were going to need it. So this is the time to get it out, because I'm just going to write this portion of the table down. Alright, so 82, 80, 82.5, and 83 and a half. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, that's all 10. So the mean of the sample means is basically this. Take all of these, add them up, divide them by 10. So 77 all the way to 83 and a half, add it all up, and divide by 10. Okay? And if you do that, you should get 80. So you should have verified that this does equal this just by simply finding the means. Okay? Now, if you forgot that table, just find out all the samples of size 2 and find the means again, just like we did in the last section. Also, letter C, you can repeat this for size 4. I gave you those as well in the last section. And if you remember, size 4, these were the 4 sample means. Here's our sample means for size 4. So this is when n equals 4. I gave you this on the last video as well. 78 and a half, 79.75, 80.25, 80 and a half, and 81. 81. And if you take all of those, and you add them all up and divide by 5, add all these up, divide by 5, you're going to get your mean of your sample means to equal 80. So it's going to be true for that as well. So no matter what the sample size is, the mean of the sample means and the population mean are going to be equal. The mean of the sample means and the population mean are going to be equal. Alright, so refer back to table 7.5. Now, if you can't remember what table 7.5 looks like, I'll write it up here for you. And that table, excuse me, it's right there in front of me. I'm sorry about that. Table 7.5 is right there. Alright, so determine the population standard deviation. Alright, so let's remember what the computing formula is for population standard deviation. So remember, it is the square root of the sum of x sub I squared all over n minus the population mean squared. So we know the population mean of this data is 80. Okay, so determine, we want to determine the population standard deviation. So we need to take our values, our values here, our x values, 76, 78, 79, 81, and 86, and we want to square those. And if you square them, 76 squared should give you this. 78 squared should give us this. 79 squared. 81 squared. And 86 squared. Alright, so we need the sum of that, though, for the formula here. If you notice this right here, we need the sum of this x squared column. So add all those up. So we're going to get 5776 plus 6084 plus 6241 plus 6561 plus 7396. and you should get 32,058. So that's 32,058 divided by 5 minus the population mean squared. Now this is letter A we're solving for here, okay? Letter A. So go ahead, divide that by 5 and subtract 80 squared. And you should get the square root of 11.6, which should give you approximately 3.41 inches for the standard deviation. Okay, approximately 3.41 inches. Alright, now, notice what letter B is. Letter B is that we want to obtain the standard deviation of the sample means for size 2. The standard deviation for the sample means of size 2. Well, we're going to use the same formula, okay? The same formula. So that part's not changing. And 80 will not change because that's still our population mean. The only thing that's changing is our amount of x's here. Because if you remember size 2, that's the table I drew on the last slide that had 10 values. If you remember, that particular table is on page 281 of your book in the top left-hand corner. Here is our sample means. 77, 77 and a half, 78 and a half. We have 81, 78 and a half, and we have 79 and a half, 82, 80, we have 82 and a half, and we have 83 and a half. Alright, so we need to figure out what this is squared. Okay? What are those squared? So 77 squared gives you 5929. 5929. I don't know why it's getting so slow on me. 77.5 squared is 6,006. 0.25. And what you want to do, continue going down through here, squaring these, and then find the sum. Find the sum of those squared. Now, you should have 10 values here. So there should be 10. So once you find that sum, plug it into the formula here. Plug it in right here. Once you find the sum, plug 10 in right here and punch this out in your calculator. Okay? And so that should give you, when you get ready to punch that out in your calculator, that should give you the square root of 4.35 if you're doing this correctly. And that's going to give us approximately 2.09 inches. Now notice what happened there. Okay, notice what happened. When we're looking at the whole population, it was 3.41. When we were looking at 2 members of the population, when we were selecting 2, a sample of 2, the standard deviation went down to 2.09. Look what happens as the sample size increases. As the sample size increases, 1, 2, 3, 4, 5, notice Here is 3.41 is when we took the regular population standard deviation. Here is when we selected 2. That's what we just got. If you select 3, this will be your standard deviation of your sample mean. If you use that table with the sample of 4 that we did on the previous slide, that would be your standard deviation of the sample mean. And when you select all 5 members of the population, there's no standard deviation because you're essentially taking the population mean at that point. So the closer you get to the closer your sample size gets to the actual population, as that sample size increases, your standard deviation is going to decrease, and that should make sense to you. As sample size increases, our standard deviation of the sample mean is going to decrease, and that should make sense because as you get closer and closer to the actual population size, once you reach the population size, you're taking the standard deviation of the population, and so you're not going to have any difference in the population standard deviation and in the sample mean standard deviation. So you have to, as that increases, as the sample size increases, the standard deviation there will decrease. Hopefully that makes sense to you. All right, so this is what we can actually say here, because there's no sense in having to go through the computing formula all the time. Now we might have to one time, but we don't need to go through it for every one of them, because we can say this: for the samples of size n, the standard deviation of the sample mean equals the standard deviation of the variable divided by the square root of the sample size. So you've got your population standard deviation divided by your square root of your sample size, and that will give you the standard deviation of your sample mean. So you'll only have to do that computing formula for standard deviation really one time, and that's so that you can get your initial standard deviation. We shouldn't have to go through it a second time like we did just a moment ago, because we can actually use this formula here. We can actually use this formula. So let's look at it. Let's try it. Let's have a little fun with it. Okay, so here's our formula. Don't forget this. All right, so the mean living space for a single family detached home is 1,742 square feet. Now that's the mean. The standard deviation is 568 square feet. For samples of 25 single family detached homes, determine the mean and standard deviation. Well, the mean is easy, because remember, the mean of the sample is equal to the population mean. So what is the population mean here? Well, I just told you it was 1742. That's the mean. So it's going to be 1742. So that's not a big deal there. Now, when it comes to the standard deviation, well, we know the standard deviation of the population. That's 568 divided by the square root of our sample size. Our sample size in letter A is 25. So this is really 568 divided by 5, which if you punch that out, should give you this, 113.6. That's letter A. Well, what about letter B? What if we increase that sample size to 500? Well, guess what? It has no bearing on the mean at all. It's still 742 because those are equal to one another. The mean of the sample means and the population mean are equal. But with our standard deviation, the difference is now we're dividing by the square root of 500, which should give us 25.4 for our standard deviation of our sample mean. All right, so that formula is going to be pretty basic, pretty easy for you to use, and hopefully you understand it pretty well. Okay. Key fact, and why is this? Sample size and sample error. The larger the sample size, the smaller the sampling error tends to be in estimating the population mean by sample mean. The larger the sample size, the smaller the standard deviation of a sample mean. The smaller the standard deviation, the more tightly the data clusters around the mean. So that's why and if the data is clustered closer to the mean, then the sampling error tends to be less. Okay, so the mean of the sample mean equals the population mean, and especially the larger the sample size, the closer it's going to get to that mean. Okay, the closer the standard deviation is going to get, and the closer our values are going to get to that mean. Okay, so hopefully that makes sense to you. If you have any questions, please ask your instructor.